All right, so let's look at this problem. Problem number 8, matrix search problem. Although I gave you at the end of last class, but we didn't have time to solve it. And I do not want to use our precious time in next class to solve it. So I use a video to solve it. First, this problem is not very hard. And actually, it just uses some simple knowledge we already know. Okay? Yeah. But, you know, the idea, some special trick is interesting. So it's better for us to learn it. All right? You need to search for a given number in an n by n matrix, in which every row and every column is sorted in increasing order. Okay? So horizontally, from left to right, the entries in each row are increasing. From top to bottom, the entries in each column are increasing. All right? Okay. So the problem, can we design a big O of n algorithm for this problem? You know, linear. We need to find a linear algorithm to solve this problem. Okay? Yeah. So at the first look, it may not be very easy because you think about it. For a matrix, it is n by n square matrix. The total number of entries for this matrix are n squared. If you look at each element once, you need n squared. But here you cannot do it. So we need to use linear algorithm to solve it. Okay? All right. So it is a popular problem in job interview. Okay? Many job interview books about algorithms, including this problem. So I also like this problem a lot. All right. Question. How do we take advantage of the structure? Yeah, the structure I just described it before, that the row elements and the column elements are sorted. Okay. So this is a critical property we need to use for this problem. Okay. So we already have this kind of experience. With the ordered structure, we know we should try to use the binary search. Okay? So the binary search, you don't need to look at all the elements. You only need to look at part of it. So why? Because you can predict. You can make very good predictions to eliminate large number of entries, elements. Okay? So here, let's use the same idea. So how to use binary search here? All right, so let's look at a simple diagram here. I use 8 by 8 square matrix. All right, so this arrow means entries along the rows are sorted in ascending order, and this arrow means entries along the columns, following this arrow direction, also in ascending order. All right. So we still use the elimination method. Yeah. So we use this method, several times before. So we have this experience. Okay. So the basic idea: try to eliminate as many elements as possible. Okay, based on the order information. So we can do that. Right. All right. So after every comparison, how many boxes, little square boxes, okay, can we eliminate? The more we can eliminate, the faster our algorithm is. Okay. All right. So we try to maximize elimination each round. Yeah. Because based on the algorithm you choose differently, the number of boxes you can eliminate could be different. Okay. So we try to maximize. All right. So here, still our main experience comes from the binary search. So in binary search, we know we compare with the element in the middle. The original binary search, we have an array. So actually, that's just a line, elements distributed along a line. So we have a position in the middle. Okay, so we can do comparison there. But here, the elements we have not distributed along a line. They are in a square. Okay? So in a square, how do we apply the binary search idea? So there are many possibilities. So we need to, take a look. All right. So here, so let me pick a point here. So A, so I choose, somewhere from the middle. Okay. So based on the binary search. All right. So we have two cases. The given key, so let's use K to represent it. Yeah. So we want to compare this key K with one of the elements in the given matrix here, A. Okay. So the first case, let's assume A less than K. If A less than K, think about how many elements can we eliminate. Okay, so can you see it? Okay, so using that order information from left to right, from top to bottom, what are those elements? We are pretty sure they are less than or equal to A, so we can eliminate them because they have no chance to be equal to K. So those elements we can eliminate. All right. So here I use this yellow square to cover those boxes that satisfy the condition. Yeah, because you can see all the elements in the yellow square, they are either at the left of the A element or above the A element. So that means their values should be less than or equal to A. Okay, along the rows or along the columns. Okay, or you can find a way, establish an inequality so that element is less than or equal to A. Okay, yeah. For example, so here, so let me just look at this. Okay, suppose we want to look at the element in this position. Okay? Based on the condition, this element should have a value that less than or equal to this one. Remember? This one. Okay? Yeah, because based on the column increasing order. Then its value based on the row condition, it should be less than or equal to A. Okay? So then we can establish the relationship between elements that are not in the same row, not in the same column with A. We can still establish that inequality. Okay? All right. So that's one. Yeah. So if you understand this, so then, so we can understand better. Okay? All right. Next. Okay. All right. Next, A greater than K. That condition. See? Yeah. Then by, the previous experience, I think you can easily identify those elements that satisfy the condition. Their values are greater than K. Okay? Yeah. So this time, this blue square, all the elements in this blue square. So we can easily show their values are greater or equal to A, and therefore greater than K. Okay? So we can eliminate all of them. All right. So this looks like a pretty good idea. So we can apply it. Okay? So we can eliminate large number of elements. All right. So, but here you can see, what's next? The question is, what's next? Okay. So how about the remaining area? The elements in the remaining area. So how do you handle that? Okay. The remaining area becomes smaller and smaller. Okay. Then the number of elements you can eliminate becomes fewer and fewer. Okay. All right. So basically we have this. We eliminate 1/4 of the current square. Suppose you have a whole square. Using this method, every time we can eliminate about 1/4 of the current square. Okay? All right. Yeah. But if you use this way, because after this, the areas become smaller and smaller, and the number of elements you can eliminate becomes fewer and fewer. And by some math calculation, you cannot show using this way, you can get bigger of n. Complexity function. Okay? Yeah. So here I do not do that math here. Yeah. Okay. Yeah. Although, so you need to have some analysis steps here. Yeah. So here I skip that part. Okay. So that means we should change a different method. All right. So we need to find a different way to eliminate elements, okay, such that so we can make sure the overall elimination is the best, not just the first few steps. The previous method, it has very good performance only for the first few steps. After that, it becomes worse and worse. Okay? So finally, the performance is not acceptable. So now we want to have a new method so we can eliminate, pretty good number of elements, and the overall performance also very good. So that's the goal. All right. So can we compare with different elements to get different elimination? Sure. So we can try, elements in different locations. Yeah. But you need to have some guideline. Okay? Yeah. So here we use another idea I mentioned before. Change a view on the problem. Okay? So we can view the problem differently. So can we, use a different angle to look at it to get a different idea? All right. So here we need that. Okay. All right. So what is the smallest element? So here, so let's explore the property of this problem a little more. So let's answer this question. In which location you can find the smallest element? So that should be easy, right? Top left corner, very top and the left, that corner. Okay? So this one, I put an S here, the smallest. Yeah, so that's easy to see. Right? So similarly, what is the largest element? Lower right corner, right? So the element at lower right corner. So now you can see, yeah. So then all the other elements, they have the values between these two elements. Okay. All right. So now next, what is in the middle between them? So why we want to ask this question? Because we want to borrow the idea from the binary search. Okay. So what's in the middle? Okay. So here, let's change the angle of view. So this time, our view will have a different angle. So you can see, the angle will be different. So this big circle, big long red oval circle, approximately covers the middle area between S and L. Okay, so you look at it. So are they in the middle? Okay. Yeah. So that means when we do our binary search, we should do in this middle area. Okay. So is that a good idea? New idea, right? So that is a new idea. So let's apply our binary search using this new idea. Okay. So now let's apply the elimination method again and see, can we improve our performance? Okay. All right. So let's start with this A point at upper right corner location. See what would happen. Okay. So if A less than K, what are those elements? We can eliminate them immediately. So can you see that? Okay. So very easy to see, right? So the same row. Okay. So the column, we cannot get any element eliminated column-wise, but the row-wise, we can eliminate the elements that are in the same row with A. So this row. Okay. All right. So that's easy. So no other elements can be eliminated. So similarly, for A greater than K, what are those elements we can eliminate? All right. So the same column. So now you can see, this property. Yeah, pretty straightforward. Yeah. So you may feel the number of elements we can eliminate may not be greater than the number of elements that we can eliminate in the first step of the previous method, right? So you can see, so that number could be smaller, yeah. But here you can see, the overall performance may not be slow. Okay, so let's see, a few more steps. Okay. All right, now let's run eliminations line by line. Okay. Each time we eliminate one line of elements. Okay. So it could be a horizontal line or a vertical line. So depends on the value of the comparison, greater or smaller. Okay. So equal, that's easy. So we find it, we stop. So we mainly focus on greater than and less than cases. All right. So we start from the upper right corner. So if we are given a, square or a rectangular area, yeah, because after elimination, we may not always get a square shape. So sometimes we may get a rectangular shape. So, but in any case, we can always find the upper right corner element. Okay, so this one. So let's start with this element. Okay. And when we do the first comparison, we can get either greater than or less than. Okay? So which of the two cases do we get? We don't know. So here we can only choose one of two cases by random selection. So either one could happen. All right, so here, just for one example, I choose the horizontal line for elimination first. So as a special example, so we just get some idea. Okay. Second, for the remaining elements in a rectangular area, so now we select upper right corner. So this red box. So let's do another comparison and then try to eliminate one row or one column. All right. So this time we still do the random selection greater than or less than. Okay. All right. So here, suppose another horizontal line is eliminated. Okay. All right. So the next step, still upper right corner element, and this time another comparison, less or greater random selection. Let's select vertical line. Okay, so the current vertical line is eliminated. So next, upper right corner selected, a comparison, random selection, horizontal line eliminated. So then the current upper right corner, red box selected, another comparison, which selected, this time vertical line selected. Next, comparison, horizontal line eliminated. Next, another horizontal line eliminated. Next, vertical line eliminated. Next, another vertical line eliminated. Next, horizontal line eliminated. Next, vertical line. Next, vertical line. Next, horizontal line. Next, horizontal line. So then we finish processing the whole square. So now you can see in this way, eventually we can find the result. Either we find that element or we couldn't find the element. So, but we will get a result. Okay. But the question is, how do you know its performance? How do you know this method has the linear performance? Can you see it? Because in the implementation, each step, there is a random selection, either horizontal or vertical. It is a random selection. So how do you control if you do not have the certainty going horizontal or vertical? How can you, get an idea how many squares have you processed? Okay? So although here, so we can find a way to see it. Okay? So for example, here, if you count, there are 14 red boxes. 14. Okay? So if you count, yeah. So in the general case, so probably you can guess a formula, right? Yeah. But here, I want to introduce another very useful problem-solving method. Actually, the way of thinking. Yeah. So also very useful in algorithms. It is called adversary argument. So here I use this example to introduce this adversary argument. So what's that? So let me explain its meaning. Okay. So we just imagine there is a smart adversary, okay, and this adversary always gives us a hard time. Okay? Yeah. Because each step, when we need to make a decision, right now we just, based on the random selection. Okay? The random selection, the certainty is so little, hard to control. We want to increase the certainty. All right. So how can we increase the certainty, reduce the uncertainty? Okay? So you cannot just do as you want. So that's not fair. So you need to find a fair way to help us reduce uncertainty. Okay? So this fair way is this adversary argument. The adversary will provide us a fair way to reduce uncertainty. Why? You can say the adversary can provide us a fair way, because the adversary has this property. He or she always gives us a hard time. What's the meaning of that? When we have two different choices, the adversary will give us the worst one. The adversary will choose the one that will make us pay more. Okay? So overall, the adversary will give us the worst case to handle. So if we can handle the worst case, then we can handle all the cases. So that's the, the basic idea about this adversary argument. Yeah. All right. Yeah, so we know, we have learned before, if we can solve the worst case, then we can solve any case. Okay? So now let's try. So what's the worst case? Okay? We will use this imaginary adversary to help us find the worst case. Okay? So let's start. Okay? Still the same point. Okay? And there are two cases. Which one is worse? Here, equally worse, right? Horizontal, vertical, equally worse. So we just select horizontal. Okay? And the next one, this location, then the two possibilities, they are not equally worse. Right? They're not equally worse. One is better than the other one. So how can you see it? Yeah. So let's see in this way. The horizontal line contains how many elements? So let's see, including the red box, 8 elements. The vertical line only includes 7 elements. So one is more than the other. Okay? So for our purpose, we want to eliminate more elements, as many as possible. So definitely we want to eliminate that horizontal line, right? But, the adversary will give us a hard time. The adversary will not allow us to eliminate the horizontal line. So the adversary will force us to eliminate the vertical line. So this time the adversary will pick the vertical line for us to eliminate. Okay? So next, equally well, so we can pick horizontal. So then next, vertical. So one horizontal, one vertical. So this will eventually give us the overall worst case. So like this. Okay? So this is the eventually, the overall worst case, right? Yeah. So okay. Yeah. So this is the worst case. So you can see. So we use this adversary argument, we can get a worst case. Okay? Yeah. So for the general case, we also use adversary argument to get this worst case, and this is certain. You can see when we do this case, there is no uncertainty, right? It is certain. So that's good. So because that's the, adversary gives us that worst case. So this is a pretty smart thinking idea. So we should learn it. Okay. So now the analysis, that's also pretty easy. Yeah, because two diagonals, okay? 2 diagonals, so we can count. So if the size of the matrix is n by n, so each diagonal has n minus 1, right? So the total, the red boxes we have 2n minus 2. Okay? So that means we only need to do 2n minus 2 comparisons. So for the worst case, we can find that element or, the result. Yeah, because we could miss that, right? All right. So this is a big O algorithm, right? So this solves the problem. So you can see, pretty smart. Okay? So not very difficult, but if you do not have the thinking like this, definitely it is very hard. All right? Yeah. So that's the solution. Yeah. So hope you can understand. Yeah. Try to learn this method. All right. So let me stop here.